Okay, so today I want to start chapter 4, which is about exponential and log functions. Exponential and log functions. So in 4.1 and 4.2, it's mainly about exponential functions. So let's define what we mean by exponential functions. A function of the form f of x equals b to the x, where b, which is called the base, it's greater than 0 and it cannot be 1, is called an exponential function to the base b. It's called an exponential function to the base b. What's really important about exponential functions is we all realize that the exponent is the variable and the base is my number. Like just to give you an idea, f of x equals x squared, that's quadratic function. F of x equals 2 to the x, that's exponential function. So you have x switched to the exponent. Once you have a variable in the exponent, then we get what we call exponential function. B in the case of exponential function is the base. It's gotta be, there's a lot of restrictions on the base. You can have a base as long as it's greater than 0 and it cannot be 1. That's very, very important. So meaning that if you look at the number line, the base can only be greater than 0, but it cannot be 1. So you have to skip 1. So the base is either between 0 and 1, or it's greater than 1. No negative base, no 0 base, no 1 for the base. Okay, between 0 and 1 or greater than 1. And we'll see why. Okay, we'll see why we have all these restrictions on the base. Okay, so if the base, so we're talking about f of x equals b to the x. If the base is 1, well, let's start with 0. If it's 0, if b equals 0, then f of x equals 0 to any power, which is 0 as long as x is not 0. So y equals 0 is the x-axis. Nothing exponential about the x-axis. Okay, if b equals 1, f of x equals 1 to the x, which is 1. Again, nothing exponential about the horizontal line y equals 1. If b is negative, why do we not accept negative base? Because look what happens. If b is less than 0, say negative 1, so f of x is negative 1 to the x. And say you want to do fractions like f of 1/2. So negative 1 to the 1/2, which is square root of negative 1, which is I, imaginary. Okay, so we cannot have negative in the base because for some values of x, you end up with imaginary numbers, and we cannot accept that when we're graphing. Okay, so that's why we have to have no 0 in the base, no 1 in the base, and no negatives in the base when we're talking about exponential functions. No 0, no 1, no negatives in the base. Okay, no 0, no 1, and no negatives. Alright, so now, if you recall, we know about exponents. So we know that 2 squared, say, is 4. If we have a negative exponent, we put it under 1. So that's 1 over 4. If we have a fractional exponent, like 4 to the 3/2, we know the bottom is the index and the top is the power. So square root of 4 is 2, 2 cubed is 8. And if you have a negative 3/2 in the exponent, it's again, you put it under 1, which is 1/8. Now, what if we have 4 to the irrational exponent? Now, what we have to do here is we have to get an estimate because we're dealing with irrational numbers, so we do it in the calculator. So 4 to the power square root of 3. And how many decimal places do you want? 4, so you put 11.03566 or 7. So what this says, I can put in anything I want in the exponent, positive number, negative number, fraction, negative of the fraction, irrational exponent. So the domain of exponential functions is all real numbers, okay? That's what this is all about. All right, so how do we graph exponential functions? Graphing exponential functions, something we did do in math 750, but we're gonna repeat today. So we're gonna talk about two cases. Why is that? Because remember the base? We said the base is either between 0 and 1, or it's greater than 1. So we're gonna consider these two cases. If the base is greater than 1, okay, so f of x equals b to the x. I'm gonna pick the easiest number greater than 1, which is 2. So f of x equals 2 to the x. I'm gonna make a t-chart. I'm gonna pick few negatives, a 0 and couple of positives, and plug them in. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. Okay, so let's graph and see what kind of graph are we talking about. Negative 2, 1/4. So this is a half, a quarter is about there. Negative 1, 1/2. 0, 1. 1, 2. And then 2, 4. So you can see how the graph is growing exponentially, and it's going to keep going like this to infinity. And over here, even if x is negative 3, negative 4, negative 5, you're still getting a positive y value, so it's never going to cross the x-axis. It's got the horizontal x-axis as, the x-axis as a horizontal asymptote, the negative x-axis. The y-intercept is at 1, no x-intercepts, and it's an example of exponential growth. So not the graph of b to the x, as long as the base is greater than 1, it's going to have this shape. The bigger the base, the faster it's going to go to infinity. Okay, let me show you with the graphing calculator what do I mean. So if I graph the one we just did, 2 to the x, and then I want to do 3 to the x, or let's say 4 to the x, as long as the base is greater than 1, and then 6 to the x, and then 10 to the x. You can see how they all have the same shape, but the bigger the base, the faster it's going to infinity, meaning the graph is getting closer and closer to the y-axis. So 2 to the x, 4 to the x, 6 to the x, and then 10 to the x. There we go, okay? They're all examples of exponential growth. So for this case, you have a handout in your notes, so look it up. There's the graph of exponential function f of x equals b to the x. The domain is all real numbers. This is what we did. This is the one we did, okay? From negative to infinity, as we remember, I showed you, I plugged in all these numbers. The range is all positive real numbers. You can see that y is greater than 0. The graph must pass through the point 0, 1, so it has a y-intercept of 1. The graph always has a horizontal asymptote. That's what we talked about. It doesn't cross the x-axis. If b is between 0 and 1, we haven't done that. If b is greater than 1, the graph will increase from left to right and is an example of exponential growth. That's what we're talking about, okay? So let's see the other case where the base is between 0 and 1. So case 2, if the base is between 0 and 1, again, I'll just pick 1/2 as an example. and I'm gonna graph f of x is 1/2 x. Remember, this is the same thing as 1 to the x excuse me, over 2 to the x, which is 1 over 2 to the x, which is the same thing as 2 to the negative x. So when we write 2 to the negative x, the base is not 2 because of the negative here, the base is 1/2. Okay, keep that in mind. So make a t-chart, same x values that we picked for the original example, and you plug it in. You have two negatives, it will be positive, so you get 2 squared or 4. Again, 2 negatives, so it's a 1, 2 to the 1 is 2, 2 to the 0 is 1, 2 to the negative 1 is 1/2, or you can plug it in there. 2 to the negative 2 is 1 over 4. So here it's going to start high and end low. There it starts low and ends high. Okay. And so y, x, negative 2, 1, 2, 3, 4, negative 1, 2, 0, 1, 1/2, 2, a quarter. So you can see how it's going down. As we look at it from left to right, it's an example of exponential decay. It has the same y-intercept, no x-intercepts. The horizontal asymptote is the positive x-axis. It's decaying, it's going down, it's decreasing as we go from left to right. The domain is negative infinity to infinity. The range is 0 to infinity. And it's exponential decay. And again, if it's 1/2 or 1/3 or 1/10 or 1/20th, it's going to have this shape. Okay? So keep that in mind. It's decreasing instead of increasing. Alright. So now let's look at number 22, page 336. 22, page 336. We have f of x equal a to the x, and it says find the exponential function f of x equals a to the x. So usually they give us the equation and they tell us to find the graph. Now we're given the graph and they tell us to find the equation. If you look at the graph on page 336, it goes through 2 points, the obvious points, negative 1, 1/5, and the one that's on every exponential function 0, 1, okay, the y-intercept. So basically, to find the exponential function, all you need is to find the base, right? We want to know what the base is. And to find the base, this is y, this is x, so we need an x and y. But if you use 0, 1, it's not going to get us anywhere. Look, if you plug in 0 for x and 1 for y, that's going to be 1 equals a to the 0. Because that belongs to every graph, so it's not going to be the differentiating one. If you use this one, when x is negative 1, y is 1/5. So a to the negative 1 is 1/5. So a is 5. Okay, because 1 over a is 1/5, so a is 5. So the base is 5. So f of x equals 5 to the x. And the graph that you see on number 22, the graph of 5 to the x, which is an example exponential growth. Okay. Now they want us to graph using shifting and translation, which we learned early on. So like number 32, it says graph the function not by plotting points, but by starting from the basic graph, and state the domain, range, and asymptote. So they also want us to state domain, range, and asymptote. Okay. So 32, page 337. So g of x equals 2 to the x minus 3. Well, the first thing is we have to know whether it's decay or growth. It all depends on the base. The base is 2, since b is 2, which is greater than 1, so it's growth. Meaning it's going to be the second graph. That's the first thing. And then it's shifted 3 units to the right. Shifted 3 units to the right. So to graph it, instead of being at 0, 1, we're going to shift it 3 units to the right. So we are going to be at 3, 1. And so instead of going like this, we're going to go, of course we can get more points, but that's the graph shifted 3 units to the right. They want domain, range, and asymptote. The asymptote is still the x-axis. Domain is negative infinity to infinity. Range is again 0 to infinity. And the x-axis is the horizontal asymptote. Okay. Which is y equals 0. The equation of the x-axis. Alright, let's look at another example. Same questions. Y equals 2 to the negative x minus 2. So remember, 2 to the negative is the same thing as 1/2 to the x. So it's an example of exponential decay. The base is between 0 and 1. It's shifted 2 units down. So it's decay shifted 2 units down. So decay, it's decreasing, shifted. So starting with the intercept, instead of 0, 1, it's shifted down to 1, 2. So it's at 0, negative 1. The x-axis, which is the asymptote, y equals 0, you shift it 2 units down. So it's going to be y equals negative 2, and then copy and paste. And it's the decreasing one. So the domain is still negative infinity, as you can see. The range, though, changed from 0 to infinity into negative 2 to infinity. And the asymptote is y equals negative 2, horizontal asymptote, y equals negative 2. Okay, here's another one. Y equals negative 2 to the x plus 3. Here, remember, we can't have a negative base, so this is not negative 2 to the power x. No, this is negative 1 times 2 to the x plus 3. That's what they mean. If they wanted this is what they would have done to have a base of negative 2, which is non-exponential. Remember, we cannot have a negative base. But that's not what I mean here. They're talking about 2 to the x. You flip it in the x-axis, and then you go up 3. So 2 to the x, which is going to be like this, you flip it in the x-axis, but then you go up 3. So let me do that. So 2 to the x, it would have been going through this. But you flip, so instead of going 0, 1, it will be 0, negative 1, and it would have been this. But that's going to be negative 2 to the x, but then you got to shift it up 3, so you start here, 1, 2, 3. So you'll be at 0, 2, right? 1, 2, 3, so you're at 0, 2. So this is shifted up there, so it's going to be in the line of the horizontal asymptote, y equals 0, it's going to shift 3 units up, so 1, 2, 3, y equals 3. And then you copy and paste. So this would be y equals negative 2 to the x plus 3. And then domain is, as you can see, always negative infinity to infinity. Range, though, it's going to be from negative infinity all the way to 3. And asymptote is y equals 3, the horizontal asymptote. Alright, there's 12 questions that I have on page 5 for you to work out, so make sure you do those. If you have any questions, shoot me an email. Next, I want to do 52, page 337. So it says if f of x equals 3 to the power minus 1, so that f of x plus h minus f of x all over h equals 3 to the x minus 1 times 3 to the h minus 1 over h. That's what they want us to show. Well, let's prove it. Let's find this expression and see if it equals that. F of x plus h minus f of x over h. If I want to do f of x plus h, I would get 3 to the x plus h minus 1 minus f of x, which is to the x minus 1 all over h. So this equals that, okay? So you can see that this has 3 to the x minus 1, this has 3 to the x minus 1. So if we factor the x minus 1 out, because I'm trying to mitigate this, okay? So if I do 3 to the x minus 1 out, then I would have 3 to the h minus 1, right? Because 3 to the x minus 1 times 3 to the h, you add up the exponents, you get this all over h, which is exactly that. So you can write it as 3 to the x minus 1, 3 to the h minus 1 over h. So it's a simple two-step solution. Alright, so now an application of exponential function is the compound interest formula. And there's a nice handout that I have in the notes for you, so you don't have to write it down. It's right here. So I'm going to zoom in on this. Okay. So A is the amount or the balance, P is the principal. What do we mean by the principal? It's the amount you invest or borrow. If you have money in a CD account or a savings account, that's the principal. Your auto loan, that's a principal. Your mortgage loan, that's principal. R is the rate per year. 3% per year, you put in there, what, 0.03. You always move the decimal 2 places to the left. N is the number of compoundings per year, which is the number of times interest is compounded per year. For instance, for banks, usually it doesn't always have to be there, N is 12, because you get a monthly statement, right? A monthly statement. So each month you get a statement, so 12 times a year. That's how the interest is added 12 times a year. If the interest is compounded, so compounded, if it's monthly, then N is 12. If it's quarterly, 4 times a year. If it's daily, 365 days a year. If it's semi-annually, 2 times a year. If it's yearly, 1 time a year. So no one is going to tell you what N is. They're going to give you those phrases and you're going to have to figure out what N is, okay? T is the, if it's 30-year mortgage, then T is 30. If it's 5-year auto loan, then T is 5. And you notice that there's also an N in the exponent, okay? So this is the formula to calculate the balance or the amount for a principal, whether it's the money you invest or the money you borrow, and under these conditions that we just talked about. Let's see an example about that. 58, page 337. 58, page 337. It says if 2,500 is invested at an interest rate of 2.5 per year, compounded daily. So when they say compounded daily, so 365 per year unless it's a leap year, okay? Find the value of the investment after the given number of years. I'll just do part A after 2 years. So if you're going to use the compound interest formula, how do we know? Because it says compounded there. So they want the balance, the principal. How much is the principal? 2,500. The rate, 2.5%. So if we move the decimal 2 places to the left, you're dividing by 100 basically. So it's 0.025. That's what you're going to put in there, okay? And the number of compoundings per year is 365. And then in the exponent, 365 times how many years did we say in part A? 2. So you can put this all in one shot in your calculator. Let's all do that so we don't mess it up on the test. 2,500, left parentheses, 1 plus 0.025 divided by 365, right parentheses, power, and then you're gonna do left parentheses 365 times 2 in the exponent, and it would be $2,628.17. So your balance, so you started with 2,500, you ended up with 26, so you found not a lot more, $128.17. But remember, the interest is very low, okay? Which isn't bad. And it's only 2,500 that you invested, so. All right. Now let's 64, page 338. 64, page 338. It says, find the annual percentage yield for an investment that earns 5.5% per year compounded quarterly. Find the annual percentage yield, or what you see as APY or APR if it's something you're borrowing, for an investment that earns 5.5% per year compounded quarterly. So compounded quarterly, that means N is 4. So if you're earning 5.5%, what's the APY or APR? It's an investment, so they call it APY. If it was a loan, then it would be APR. Remember, sometimes they tell you, oh, your mortgage loan is 3%, but then APR is 3.25%. How do they figure that out? So we're using this formula. So after 1 year, the principal will grow to, so what's the principal going to be? P is 1 plus 0.055. Why 0.055? Because you divide it by 100, or you move the decimal 2 places to the left after 1 year. So 4 times a year, and N is 4 times 1. So it would be 1.056145P. And that's gonna give you your percentage yield right there. So you can figure out what it is. If you minus P from that, you're gonna end up with 0.5145, which is 5.6145%. Okay, so you figure out how much you're gonna have after 1 year, and whatever you get, you minus P from it, and it's gonna give you the annual percentage yield. Okay, that's the easiest way. There's a little bit different way, but this is easier. You just, whatever you get after figuring out what happens after 1 year, then you minus P from that. It's gonna give you the answer. All right, so that ends 4.1 until 4.2. Have a good day.